So we talked about inverses in Algebra 2. We talked about a little bit at the beginning of this year. So inverses in general are anything that undoes another function. So the inverse of x squared is the square root of x. The inverse of adding something is subtracting it. So we're looking at undoing, right, the different operations. Now remember that our that our trig functions are still functions. They're still operations. So we can still undo them if we have an inverse. Okay, but we do need to do a little bit of remembering of some key values or some key vocab before we can get into that stuff. So do we remember what a 1-to-1 function is? So remember that a function has to pass which test? The vertical line test. So that's basically like step 1. And we have all different types of things within functions. Then within that category, we have an even more specific type of function that's called a 1-to-1 function. And it is a function where the inverse of a function is also a function. So if we think of an example, we could think about that x squared. So y equals x squared. What does its graph look like? A parabola, agreed. So it looks like that. Now, what did we say that its inverse was? Okay, almost. Because remember, if we wanted to find the inverse, we would switch x and y, solve for y. So we would take the square root of both sides. But when we take the square root, what do we have to add? Plus or minus. Plus or minus. It's actually plus or minus the square root of that. So our graph ends up looking something like that. Now notice, is our square root of x graph, because now plus or minus, is that a function? No, right? Because it doesn't pass our vertical line test. So we could say that the square root of x is not 1-to-1. Because its inverse is not also a function. Now, just like with our vertical line test, there's actually a way to check to see if a function will be 1-to-1 from the very beginning. And it's called our horizontal line test. So horizontal line can pass through more than one point. Now with me? So let's think back to this graph. If I were to draw horizontal lines through my x squared graph, does that pass my horizontal line test? Horizontal lines? I can't pass through more than one point with horizontal lines now. No, it doesn't, which is why it's not 1-to-1. Well, let's think about a different graph. Like if we had our y equals x cubed graph. That looks like that. graph is nice and pretty. Does that graph pass our horizontal line test? Yeah, so remember we only have one point at 0, 0, and it increases really, really slowly and decreases really, really slowly, but there's still not any points that are going to be actually horizontal to each other. Does that make sense? Now they're going to be like 0.001 away from each other, but they're still not technically like across from each other. Does that make sense? So this one would be 1 to 1. We all with me? And the reason that we like 1-to-1 functions is because we like things that are functions. They make our lives easier. So if we have functions that also have an inverse that's a function, we're able to do more things with it. And sometimes, we're going to look here in a second, we have to have an inverse that's a function in order to be able to use it. Alright, so now remember that our inverse function, we kind of talked about like generally what it means as far as it kind of undoes the other stuff. Remember that our like strict definition is the inverse f inverse of x is the inverse of f of x if and only if f inverse of f of x equals x, which also equals f of f inverse. So remember that because they're inverses, they undo each other, and I'm only left with x, and that has to work both ways. So remember, I'm taking the composite, and I have to be able to take the composite either way, and they undo each other. Yes? Questions so far on that? Okay. So, like we were talking about, we also have inverses for our trig functions. So, we're going to start with sine, and then we'll look at cosine and tangent later. So the way that we write this notation, okay, so our original function, remember, is y equals sine of x. Then our inverse function, we either write as sine inverse of x, or we write it as arc sine of x. Now both of those mean the inverse of x. The sine to the negative first is like a more current notation, and you'll see that one with like newer textbooks and things like that. The arc sine is a little bit like an older notation, so sometimes like you'll see it with older textbooks, or like on the ACT, sometimes you'll see questions that say like arc cosine, arc sine, and it just means the inverse of sine. Now, we need to think about our graph, because like I said, remember we're looking for the inverse sine function. So we need our inverse to be a function. Well, what does that mean that sine has to be? Just like so in order for the inverse to be a function, the original function has to be
the inverse of.
So in order for the inverse of a function to also be a function, our original function has to be 1 to 1. Are we all with me? So we're wanting to make sure that sine is 1 to 1, so that way our inverse will also be a function. Yes? And we said an easy way to look for that is our horizontal line test. Yes? So we're going to look at the graph, which hopefully now we all know how to graph our sine graph. We should be experts at it. We're going to look at our graph. So we're going to graph y equals sine of x. So what is sine of x at 0? 0. And then remember that we're going to go all the way out to 2 pi, right? Halfway in between is our other 0. Halfway in between that is going to be our maximum at 1. And then halfway in between our second 2. But does our graph stop there? No, remember it continues on forever. And we know that it continues on in that same pattern. Okay, so we're again trying to see is sine 1 to 1. So does our sine graph pass a horizontal line test? No. Does it pass it anywhere on our graph? No, because remember our sine graph is a periodic function, it's going to repeat its point over and over and over and over again, which means that it's not going to pass the horizontal line test like anywhere. Alright, all with me. Which again, doesn't mean that it's impossible to use our inverse sine, but we are going to need to like manipulate it a little bit. Yeah? Okay. So let's go back to our y equals x squared graph that we looked at. So remember we said that y equals x squared is not 1 to 1. Well, we want to see, okay, is there maybe just like a portion of our graph that we could look at that would be 1 to 1? So, notice that what's causing the problem for my square root graph is that we have the positive and the negative graph. Yes? So if we just looked at just the positive or just the negative, that would be a function. Agreed? Well, because most of us like dealing with positives more, we're just going to look at the positive portion of our graph. Y'all okay with that? So, if we're just looking at the positive portion of our square root of x graph, we need to go back and look at, okay, for my x squared graph, which portion of that graph would give me just the positive portion for my square root? What do we get? The left side or the right side? Left? Sure? Sure. So remember that here I would have, so say, like if I just had a point, right, I'm dealing with x squared, so we would have like negative 2, 4 on our graph, right? So in order to be able to find the inverse of that, I would have to be able to flip that, agreed? Which means that 4, negative 2, negative 2, 4, negative 2 would have to be on my inverse graph, right? So I know that the stuff on the left side would give me the bottom portion of this. Yeah, with me? So that would be like this point then. Again, remember we're trying to restrict it, so we don't want to use that point. We want to use this side of our graph instead. So the positive x squared portion gives us the positive square root of x. So now let's think, okay, if I'm just looking at my red graph, does that pass my horizontal line test? Like if we pretended the rest of the orange graph wasn't there, and we just looked at the orange graph, does that pass the horizontal line test? Yeah, so now we could say, okay, if I just look at this piece of my x squared, it would be 1 to 1. Okay with that? So what x values are we looking at here? So where's our vertex at? 0. And then we're going to continue on through infinity, right? Does that make sense? So basically we said, okay, I'm going to chop off half my graph, because now if I do that, I will be 1 to 1. And that allows us to manipulate things a little bit easier because now our inverse would also be a function. Agreed? So we want to do a similar thing for our inverse sine function. We want to chop off a piece of our graph so that it will pass our horizontal line test, which would mean that our inverse will also be a function. Agreed? So what portion of the graph do we want to use? So one of the parts that goes like that, agreed? Because we want to try and include the full range, meaning we want to go from -1 to 1. We want all of those values included. Okay? So where's usually a good spot to start that we like? 0. Okay? So notice that I include 0. Okay? Starting at 0. I'm going along. I'm okay so far. But what happens once I get to my maximum? It comes back down. So if I come back down, would I pass my horizontal line test? No. So we know we can't keep going. Well, technically, we could skip to like that next 0, right? And go down from there. But then we have like a really weird like break in our graph. So we don't really want that either. However, notice that instead, if I go backwards, right? That portion of the graph would pass my horizontal line test, and now I'm including all of the values from -1 to 1. We're okay with that. So, what portion or what x values am I looking at here? So remember, I'm going to end at 2 pi, which means that halfway in between is pi, so then halfway in between that is
pi over 2.
Pi over 2. So each one of my boxes represents pi over 2. Okay, so what's that mean that my minimum is at? -pi over 2. And then my maximum is at pi over 2. So I know basically I chopped my graph off from -pi over 2 to pi over 2. We're okay with that. So now when I rewrite my sine graph, what I'm actually saying is I only want to use the portion of my graph where my domain is -pi over 2 to pi over 2. And then what is the range of our sine graph? Agreed. So -1 to 1. You okay with that? So notice that my input here are angles, and my output are just normal numbers. I mean, those numbers have to be between -1 and 1, but they're just numbers. Yes? Okay. Now remember, before we find our inverses, we swap our x and y. Well, if we swap x and y, what does that also swap? Our input and our output. Yes, which is also our domain and range. So what is our domain now for our inverse of sine? Yeah, it just becomes the range of my original, which means that my range of my new function is what? Yep, -pi over 2 to pi over 2. And again, because we've switched it, basically we're going opposite now. So our inputs are just going to be numbers, and our outputs are going to be angles. So we're kind of working our way backwards. So we're going to start with a number and say, what angle of sine gives me that number? And that would be. Does that kind of make sense? Okay. Now, for the most part, I'm not going to ask you to graph your inverse graph. Like you're not gonna have to do transformations with it or anything like that. But I do think it is nice just to at least kind of look at it. So our inverse graph looks something like that. Okay. So notice that it looks a lot like our just normal sine graph, like the portion that we like chopped off, right? Because remember that our inverse is always a reflection across what? Do you remember?
Y next Y.
There you go, yes. Y,
It was correct in my head.
I got you. Y equals X. So notice that if we were to draw these two graphs, they intersect at 0, 0. Notice that my red graph is kind of, like again, if we just like flipped it, we would get that blue graph. But because our blue graph is so close to that line, that's why they look so similar. The farther away that you get from that line, the more different that they're going to look. So really, the only difference for ours is that like instead of kind of curving the other direction, right, it curves down instead of up on the left side, and then instead of curving kind of back over, it curves up and side. But they look kind of similar. Again, remember, you're not going to have to memorize those or anything like that. I just wanted you to see what the graph looks like. So if I graph that, pretending that my graph is nice and pretty. It looks something kind of like that. But again, we don't have time to graph. Okay, questions on that? So for us, for the most part, what we're going to be dealing with is not like graphs of things. What we actually want to do is like use our inverse to evaluate different types of functions, or to help us with like word problems. When instead of finding a side, we want to find an angle, right? And in that case, we want to use our inverse function instead of our normal function, okay? But we do have to be careful. Because of that requirement, okay, what did we say our ranges have to be between? What did our outputs give? Yeah, negative pi over 2 to pi over 2. So that's what we want to stick with, is negative pi over 2 to pi over 2. Now let's think about if I was looking at my unit circle. What two quadrants have angles that are between negative pi over 2 and pi over 2? So from my x-axis to my positive y-axis would be 0 to pi over 2, right? But then what's going to give me those negative angles? Which direction are we going to go?
Down.
Which is
Clockwise.
clockwise, right? And those are going to give me my negative angles. And to get to negative pi over 2, that would be at our negative y-axis. So we're specifically looking at angles in my first and my fourth quadrant. We always do. Okay. So now, if we think about arc sine, so remember arc sine is just another way of saying inverse of sine, okay? We're wanting to work our way backwards. So we're plugging in a number, and we want to think in our heads, what angle gives us sine is negative 1/2. So let's think about just in our first quadrant, right? It would be positive. Okay, so if we just looked at the positive 1/2, which of our first quadrant angles gives us a positive 1/2 for sine? Well, we know it's not pi over 4 because that's square root of 2 over 2, right?
30 degrees.
Okay, so what is that in radians?
1/6 pi.
Pi over 6. So, we know that sine is negative in our third and fourth quadrant, yes? So we're looking for angles that have reference angles of pi over 6. So what angle in our third quadrant has a reference angle of pi over 6? Remember, it's 1 bigger than our denominator in our third. So that would be 7 pi over 6. Okay. And then in our fourth, it's 2 times the denominator minus 1.
13 pi over 6.
11 minus 1, not plus 1. So 11 pi over 6. But again, we always have to think back to that range of numbers that we're allowed to have our answers in. Is 7 pi over 6 or 11 pi over 6 within negative pi over 2 to pi over 2?
11 pi over 6 is 50.
Okay, so 11 pi over 6 is in the right quadrant because it's in the fourth quadrant, right? I agree. However, notice that like it would technically be like over here after my pi over 2. Does that make sense? So we kind of need to think about how can I convert it or find the coterminal angle, right, to get the negative angle that would be in the same spot. Now with me? So we still want that same angle of 11 pi over 6, but we want to find the negative coterminal angle. Alright? Negative pi over 6? It would be negative pi over 6. So remember that if I'm talking about this angle right here, to go counterclockwise gives me the 11 pi over 6, which means that the like small leftover portion to get to 2 pi would just be pi over 6. That would complete the whole 2 pi. However, because we want to go backwards or clockwise, we put a negative in the front of it. Does that kind of make sense? Y'all with me? So it's the same spot on our graph. We get the same terminal side, but now it's within the required range that we decided we had to have. Yes? Okay, so let's look at another one. Again, this time it gives us sine inverse with the negative 1, but again, remember they mean the same thing. So this time, I'm thinking, what angle gives me sine equals square root of 3 over 2? Yeah, so it's going to be the opposite one, right? Remember, it's not going to be pi over 4, because that's square root of 2 over 2. So it's going to be the other one. So we know pi over 3 would be the first time that it happens. It's also going to happen in our second quadrant. At what angle? Yeah, so it's 1 less than our denominator. But again, remember we want our answer to be in this interval. So which one of those is in that interval?
Pi over 3.
Pi over 3. And this time, because it's already between negative pi over 2 to pi over 2, we don't have to change it, which is kind of nice. So really the only time that we're going to end up having to change things is when we have negatives. We're basically going to have to look at, okay, what is the clockwise angle that would give me the same thing? Okay? So then lastly, we're thinking, okay, what angle for sine gives me out 2? So let's go back to our sine graph, right? My input at 0 is 0, but my output is still 0, right? So because we're going backwards, basically we're looking for an output of 2. So what x value gives me an output of 2? None. Which means that notice that our domain for our arc sine is in between negative 1 to 1. Which means that 2 is outside of that domain. So kind of just like if we had a square root and we tried to plug in a negative 4, we would say that it's undefined because it's outside of the domain. This is also going to be undefined because it's outside the domain of what we're allowed to plug in. Does that kind of make sense? Yeah. Questions so far? Alright, we have one last example to look at. So remember, back to when we were talking about inverses, the whole thing that makes an inverse is that they undo each other. So if I take sine inverse of sine of x, they should undo each other, and I just end up with x. Also, vice versa. If I have sine of sine inverse of x, they will also undo each other. And I'll just get what's on the inside. Kind of with me? The only kind of tricky part is that they still have to be within that range that I talked about. Does that make sense? Like here in the example that they give us, our arc sine and our sine would undo each other. So we get 5 pi over 3. The only problem is 5 pi over 3 is not in that range that we had, right? So they still have to be between negative pi over 2 to pi over 2. But 5 pi over 3 is in which quadrant? It's in our fourth quadrant. So what's the leftover piece going to be?
5 over 3.
Yeah, pi over 3. But again, remember, we want to go the opposite direction, so our answer would just be negative pi over 3. So they still undo each other just like always before. The only difference is sometimes we might have to think about, okay, is this in the right range from negative pi over 2 to pi? Any other questions? Concerns? Comments?